In a digital communication system, it is possible to define probabilistically different channels, taking into account different levels of abstraction about what we consider a channel. And every channel will have a different input and a different output. The first level of abstraction is the Gaussian channel. In the Gaussian channel, what we have is the channel that relates the transmitted signal and the received signal. This is basically modeling the transmission medium. Now we are going to analyze this channel. In the Gaussian channel, the input is going to be the transmitted signal, and in our probabilistic model, what we consider the input is the value of the transmitted signal at a given instant, for instance t0, and the output of this channel is the value of the received signal at the same instant. The reason for the name Gaussian channel is that in the simplest possible model, the received signal is considered to be equal to the transmitted signal plus thermal noise. And the statistical model for the thermal noise is a random process that is stationary, ergodic, wide, and Gaussian, with zero mean and power spectral density and 0 halves. With this statistical model, the noise power is infinite, and to limit the power of the noise, power, usually at the input of every receiver we have a noise filter, and this noise filter has been included in the definition of the Gaussian channel. To consider the best possible case, ideal filters will be considered, and this filter will be an ideal filter with bandwidth b Hz, the bandwidth of the transmitted signal. If we filter thermal noise with an ideal filter of a given bandwidth, the noise power is n0 times the bandwidth in Hertz of this filter. Taking this into account, now we can introduce the probabilistic model for the Gaussian channel. The input is the value of the transmitted signal in a given instant t0. The output of the probabilistic model is the value of the received signal in the same time instant, and the probabilistic model is the conditional distribution of the output given the input. And taking into account that we have Gaussian noise that has power n0 times b after the filtering, the conditional distribution of the output given the input is a Gaussian distribution whose mean is the input, the value of the signal at t0, and the variance is the noise power n0 times the bandwidth in Hertz of the transmitted signal. In the next level of abstraction, the modulator and the demodulator are included in the definition of the channel. And now the channel is the channel that relates the vector representations of the signals in the different symbol intervals and the vector representations of the received signals in the different symbol intervals. And this is called the Gaussian channel with digital input. For the probabilistic model of the Gaussian channel with digital input, the input of this channel is the vector a of n that is transmitted at a given instant n. This is, in general, a vector of dimension capital N, and we have an alphabet of capital M possible values. And the output is the vector q at the same discrete instant n. And basically, the Gaussian channel with digital input is equivalent to the equivalent discrete channel that was introduced in chapter number 3. In the context of the information theory, there is a different name, but both channels or both definitions are totally equivalent. And in the equivalent discrete channel, we saw that the relationship between the vector that is transmitted and the vector that is received is just by the addition of a noise vector. A noise vector with independent components, and all these components are Gaussian, zero mean, and with variance n 0 halves. Therefore, the conditional distribution of the output given the input is this conditional distribution of the observations given the transmitted symbols. And for a symbol AI, what we have is a Gaussian with mean AI and variance n 0 halves. Now, in the context of information theory, only a small change in the notation is used, and instead of Q and A, we have Y and X, random variables, generical random variables. But the probabilistic model is the same one as the equivalent discrete channel that was seen in chapter number 3.